Good afternoon, everyone. I'm Kavana, Marketing and Media for Messen Labs. So, firstly, thank you all for joining this webinar on optimizing power supply designs with Altair PSIM. So, to begin with, I would like to introduce Messen Labs, a leading provider of simulation and analytic solutions for the engineering community in India and a proud partner of Altair. At Messen, we work to help clients boost efficiency and also to achieve excellence in their engineering projects, bringing together expertise in simulation software and data analytics to deliver innovative solutions. Additionally, we also have our skilled engineering team, which is all set and ready to make the unique ideas of our valued customers, establishing us as a leader in virtual product development. So now to kick off this webinar, I would like to introduce Mr. Simak, an application engineer specializing in PSIM at Messen Labs, who will be our presenter today. I hope you find this session valuable. And if you have any questions, kindly drop it in the chat box and Mr. Simak will address them at the end. Thank you. So now over to you, Simak.
Thank you, Governor. Good afternoon, everyone. My name is Mohammad Simak, and I'm the application engineer working on Altair's electrical and electronics domain software at Messen Labs. And today we will be focusing primarily on PSIM. The webinar is titled Optimizing Power Supply Design with PSIM, and we will be getting straight into that. So just a brief about Messen Labs. As Kavana mentioned, we are the leading simulation and analytics solution provider to the engineering fraternity in India. We are a channel partner for the Altair Engineering Company. And coming to the domain and the industries that we serve, they are wide ranging, straight from automotive, aerospace, education, energy, financial services, government and defense, heavy rail, industrial goods, material suppliers, and so on. These are just some of our clients, Altair's clients across the globe. And this is to give you an overview of the software solutions that we provide. As I mentioned, we provide solutions across domains and across industries, and we are broadly classified into three divisions: the data analytics stack, which contains our different tools for enablement of AI ML model development, and further on the high performance computing and so on, and then the simulation stack, the different type of simulation software ranging from power electronics, mechanical to electromagnetics and so on. Similarly, we have the IoT stack as well for the IoT applications and embedded systems development. And finally, we have our offering known as the digital twin, which we can make by combining all the different products from all these three stacks. So by putting the products and technologies from all of these stacks together, by the convergence of technology, we are able to come up with this digital twin technology, which is basically a digital replica of the actual hardware, and then we are able to analyze more in the software in the digital replica, and then the results will be very accurate to how it would have been if we would have conducted experiments in real life objects. So that is the entire idea of this digital twin, which is possible by the convergence of all our technology. So this was the brief overview about the Altair software portfolio. And now jumping straight into today's topic at hand, which is PSIM. So just a brief about power electronics. So power electronics, as we all know, basically deals with the conversion and management of electrical power, and its applications are pretty much everywhere these days, ranging from control systems, control drives, and across industries, across applications, from the smallest of devices like the mobile chargers to large large electrical appliances. Power electronics is found everywhere. And focusing purely on the conceptual basis of power electronics, if I could put it in a way, the future of power electronics would basically involve, the thousands of switches, or multiple number of switches turning on and off multiple times, like thousands of times in a very short span of time. So this is what is the whole heart of power electronics is focused on. And when this happens, derivatives are induced into voltages and currents, and these are what have to be solved. And PSIM specializes in solving these derivatives without any convergence issues. So it's a simulation software which is focused on solving these derivatives which come in power electronics applications, and it is known for its accuracy of results and the speed of its simulations, and how robust the software is. And now, just to give you a brief background on PSIM, the software specifically designed for power electronics. So we've been the leading simulation tool for power converters and motor drives, initially positioned as software between a device or circuit level simulator such as SPICE and a control level software such as 7. So we intended to bridge the gap between these two softwares. So we initially positioned like this, and as I mentioned earlier, PSIM is known for the speed of its simulation, the lack of convergence issues, the accuracy of the results, and the entire robustness of the software. And we provide different levels of fidelity as well. I will get to that later in the session. And now this is to give you a brief overview of the entire PSM ecosystem. So right at the center, you can see under the simulation we have as I mentioned, main focus is on power electronics. We have renewable energy components as well for your renewable energy simulations. Like we have battery models, ultra capacitors, and wind energy components as well. We have special devices for the rapid thermal loss calculation of your switching devices. We have control elements for digital and analog control. And then we have motor drives with different inbuilt motor machine models which you can use for your simulation. And then we have our own code generation feature as well. So it is basically just a one-click process. So once your entire power stage and control stage is designed, once you just click on generate code, the software will will convert your control logic into the code, and it will flash it into your hardware target. So that we have that supported as well. And then for anyone interested in doing VHDL or Verilog code, we provide co-simulation support with the Model Sim software. And similarly, with pretty much any third-party software which supports functional mockup interface or FMI, PSIM can be linked and used with. And then so we have a lot of support for co-simulation with other software as well. Similarly, initially at the design, you can see this smart control and readily works. It will enable you to These tools will enable you to design your power converters faster along with PSIM. And at the bottom left of the screen, you can see this design suits. So these are some of the most recent additions for PSIM. And in these, basically, we provide a set of templates, not just templates, but in the templates for each template contains unique capabilities. It is to enable you to fasten up your design process. You need not start any design from scratch. A lot of the work has already been done for you with just the bare minimum of input values. You can proceed with your design, and the software will do the rest for you. So that is the entire idea behind this design source, which we will get into more detail right now. So this was about the brief overview of the entire PCM ecosystem. And just to give you a brief about the entire Altair's power supply applications, we have software for power supply design, which we are looking into right now, PSIM. And then similarly, we have tools for the thermal and PCB board level analysis as well. And then for motor application as well, the controller design and the control stage part can be easily done in PSIM. Whereas if anyone is interested in designing their own motor and the entire multi-physics design behind the motor, then we have software that support that as well. And then finally, for the entire system level simulation, we have a software known as Twin Activate, wherein we do our digital twins as well. So now I'll just show you the name of the softwares which I spoke to you about. For thermal, we have SimLab, and for PCB board, we have Polix, and for the parasitics, we can do it in Flux. And this was about the our entire motor control design application. Initial motor design, we can do it in Flux motor with further electromagnetic analysis in Flux and CFD in SimLab, and the entire NVH and structural side of things in OptiStruct. And then we can take that particular motor model, as it will have much higher fidelity to the PSIM software, and we can do all the controller stage design in that. And then overall system level simulation can be done in twin activate. And we have a software called as embed, which particularly for rapid prototyping of embedded systems and code generation, which can be used as well in this entire design process. All right, now coming straight onto the power supply design suite. So as I mentioned to you, these design suites will enable you to skip a lot of the work. So once you just open any one example or a topic from the design suite, and what you see in the screen is what will open for you. You can see the circuit already completely done of a full bridge resonant LC converter in this case. And then towards the left, what you see are all the inputs that you need to enter. You see the DC input, output load, operating conditions. So those are all that you have to work on. So once we've entered these particular values, and all we have to do is click on update parameter file. So that will calculate all the remaining parameters. It will enter it into the circuit as well for you. So after that, we just have to click on run simulation, and we can analyze the results. It is so simple and straightforward. It will reduce your work to a matter of minutes basically. And the best part is each type of example will come with its own unique feature. So for further analysis. And for example, in this one, resonant LLC converter, you can see the design curves and the steady state waveforms feature, which you can view and analyze even before running the simulation. Post simulation, of course, we can do more. So furthermore, we have more examples such as buck converter, boost converter, and so on. I'll show it to you in the software itself at the later stage of this. So, but this was the entire idea about the power supply design. So and now coming to our EMI design suite, EMI filter design suite. So this is the most recent addition to our design suites, and this is in a way slightly unique as well, because in the regular the electronics, the system design process, the EMI filter design and the EMI analysis has traditionally been done at the end of the PCB design stage for most cases. So what the idea behind bringing this feature out was that to enable users to give users a platform so that they could do an initial level of EMI analysis and EMI filter design at the schematic level instead. Hence, later when they do the final design at the PCB design stage, a lot of the work will be done, and it will be much easier. So this was the entire thought process behind bringing the EMI design suite out. So that at the initial schematic level itself, you can do your EMI analysis, and you can do the filter as well. And as it is a part of the design suite, the software will do a lot of the work for you again. So it depends on our inputs. The inputs based on the actual hardware testing values what we have obtained, or the theoretically expected values. So the more accurate our inputs, the more accurate the software will provide the results, and then we can compare it as well. So without the filter and with the filter, what the state of the our EMI levels, EMI and common mode and differential mode levels are. As you can see towards the right of our screen, without the filter, we can see that the levels are overshooting the standard. So the CISPR 25 is the standard which it should not cross. And then with the filter at the bottom of the screen, we can see that it is it is well within the limit. So this was the entire idea behind the EMI design. So these EMI components are there to do it, and then we similarly we have a few examples as well, which you can directly examples and templates which you can directly use and continue on with your work. And now coming to motor control design suite. So motor drives is another, along with power electronics, the second part which PSIM specializes on is motor drives or motor control. So we have a long list of of motor systems ranging from PMSMs, BLDC, synchronous, and so on. So we can just take any one of them, and similarly, in the design suite, we have many different control algorithms done. The logic is already entered in the software for you. So we just again, as similar to the other power supply design suite, which is the bare minimum input values such as the DC bus or inverter switching frequency, and then the load, torque load, and then the few of the motor parameters and some of the motor controller parameters. We can, we can have our design set in minutes, basically. The software will do all of that for us. So we should just select the ones which we want to use, the logic which we are looking for. Currently in this example, they've done it with MTPA, field weakening, and NTPV, and then we can go ahead. I will show an example with the FOC control technique towards the end of the session once we're in the software. So this was about the motor control design. So as you can see towards the right, we have the three-phase currents, the reference torque, and the sorry, the reference speed and the speed of our system, and then the torque of the motor, and then at the bottom you can see the flag at what instant of time, at what logic is the system running on. So all of this we can see. The software we don't have to do anything extra to view these outputs. Once we run the simulation, the software will give you the option. We can pick and choose whatever we want to see and analyze and post process and so on. Now coming to the HEV design, so this is similar. The logic remains the same. We have different types of HEV powertrain systems, and then with the bare minimum inputs, we can simulate and we can analyze the results. Now coming to the different fidelity models, what initially I had mentioned. So here we have ideal switches and three levels of switches: level 1, level 2, level 3, and we have these devices known as thermal models as well. So depending on our application, depending on what application and what purpose we are doing our simulation, we can choose to use these switches. So the fidelity models go like this: the ideal switches are as the name suggests, they're ideal, and as the fidelity increases, it'll be more realistic. More of the parasitic inductance and capacitance values can be entered into these models, and you know uh, the output can be further analyzed, such as switching transients and so on, and the switching loss calculations. Now coming to how do we choose to use them? The ideal switches can be used for most cases. For 90% of our simulation applications, we can use ideal switches, such as for control stage design, for for confirming the control stage designs, for confirming our inductor capacitor values. For all of this, we can use and our entire circuit level working. For all of this, we can use ideal switches. It is sufficient. It will get our job done for us. Now, coming to our higher level switches, level 2, level 3, when we are particularly interested in doing the switching loss calculations, and to finalize which device we want to use in our circuit, whether be it which MOSFET or which IGBT or which silicon carbide devices, then in that case we can use these higher level devices, wherein we can and wherein we can use parameter values or the data sheet values from the actual manufacturers to model these. So modeling this is very straightforward. Only a few set of parameters from the data sheets will have to be entered, and with the name of the device we can save it and we can use it. So for those simulations and for the EMI, when all the extra parasitics are being considered, so for those we can use these higher level switches. And now finally we have the our thermal switches. These are for quick loss calculations. So behind the scenes, these thermal switches like pretty much 90% ideal switches itself, but they are meant for fastening up your, well, if you want to find out your let's say junction temperatures, and then the switching losses. What the higher level devices provide you at the end of the simulation is are more outputs, whereas these thermal models will focus solely on this initial thermal level output, and a few switching losses as well. So it is basically, the whole idea is to save time. So in if you're focusing solely on an application which the thermal device can help you with, then we can go ahead with those. It will save time in of the simulation in comparison to the level 1 and level 2 devices. As we know, the entire point of us doing simulation is for efficiency. So this was the idea behind it, to save time and for quicker loss calculation. And then, as I mentioned earlier, we have various motor models like PMSMs and BLDC, synchronous models, machines, and so on. And then we have in our renewable energy library, if I can put it, we have batteries, we have ultra capacitors, we have solar cells, we have wind turbines, which we can use in our simulation models. And then we have different magnetic modeling blocks as well for magnetic modeling, for modeling transformers and so on. We have many different types of transformers as well. But if you would like to model your own, we can do that as well. Different levels of fidelity included. This is what I earlier mentioned. So initially we have the ideal devices, and then we have the level 1 or level 2, and then we can import and use spice models as well. So depending on our application, we can use them. And this is just a comparison of the output results obtained when a spice device is used, and which you can see it in blue, and then you can see red is our PSIM's answer to that, which is the higher level devices, which is in this case level 2. So you can see that the values are pretty much the same. So the higher level devices are our answer to the spice devices, basically. And another advantage of using these high level devices or in a simulation is, while the while these while our model is simulating, we can change the values live as it is simulating, and we can see the change in the output as well as it is simulating. This will be possible if we can use the higher level devices or ideal devices as well. And we have a list of microcontroller libraries, which you can just drag and drop and use it in our simulation. So this is just an example of a backup power supply using two microcontrollers. That's all this is meant to show. And then for moving further in our motor drive simulation, we can generate efficiency maps. We can generate entire efficiency maps for the entire motor, inverter, and the entire motor drive system. So we can see at what at that temperature and at that speed, what is the efficiency of the system, and how much losses is taking place and so on. So these efficiency maps can be generated as well once the entire simulation is done. And now for this is a device database for quick loss calculation. The thermal models are stored here. There is an inbuilt library of models from many different manufacturers, but of course we can enter our own as well if there is a manufacturer which a model which is not available here, be it a MOSFET, IGBT, or anything, even an inductor for that matter. We can enter it here as well. Similarly, for the thermal loss calculation, we have this feature called as the curve capture tool. So wherein we can directly, in a way, trace the curve from the data sheet, and we can save it into our software. And this will be used again for the loss calculation of the thermal models. So very easy to use and fast feature. So here you can see in the example that the curve has been traced exactly, and it has been stored into the software. So then we can use this. So this is just another example of the same. And this is just a example of a three-phase inverter loss calculation, which has been done in PSIM using the Infineon hybrid pack switches, and then you can see the circuit here. And then so once we simulate this, you will get these outputs. You can see the conduction losses, the switching losses, the efficiency, the junction temperature, the three-phase currents, and so on. And so for all of these outputs, we don't have to put any additional probes. The software will do it. And then similarly, coming to magnetic modeling, we have, as I mentioned, we have a list of inbuilt transformers as well, but we have like components such as winding, air gaps, linear cores, saturable cores, and so on, so that we can model it on our own, and we can model magnetics of any complexity basically. And then now coming to the code generation part. So here again, as I told you, it's literally like a one click process. So once our power stage is design is done. So in this example, we can see that it's a PMSM drive with sensorless FOC. And then once we click on the code gen feature option, the software will convert our control logic into the code. It's an auto generated code, and it will be flashed into our hardware. And then we can for rapid control prototyping, and we can analyze it further. So these code generation feature is supported for Texas Instruments boards. And similarly, we support the power processor and the loop simulation as well. So we can test and debug the control code. So the control code is running on the hardware while the power stage is simulated in PSIM. Similarly, we support post simulation with MATLAB Simulink. So for example, we can do the power stage in PSIM and the control part in Simulink. And similarly, we can do co-simulation with the other tools wherein motor design is possible. As I mentioned, Flux, and we can bring the motor model here and we can do it. As I mentioned, for VHDL or Verilog code, we can co-simulate with Model Sim. That can also be done. And these are just a few testimonials before we jump right into the software. So here we have a testimonial by Mr. John Miller, the consultant former director of Power Electronics and Electric Systems Research Center at Oak Ridge National Labs. So they were using it PSIM actively for the conductive and wireless charging of light and heavy duty vehicle applications and more. So here you can see what he's mentioned. And then we have a testimonial by Mr. Kevin Lee, Chief Engineer of the widely known company Eaton. So they use it extensively for their motor drive applications. And here we have by Mr. Amir Ranjpar. He's a senior technical fellow, electrification HV electronics at Kano. So here they've mentioned about how PSIM has basically been used and it's helpful for the inverter level applications, inverter applications. And similarly, we have a testimonial by Mr. Michael Shriver, who's the engineering section head of the moved aircraft group. So they have been using it actively, again, for their motor drives applications. And that, as he's mentioned, the power and control element modules have been quite helpful. So this was about my presentation, and now we will go straight into the software. So this is the PSIM software. as you can see here, the, as you can see the interface here. Here you have the file, and if you want to open a new worksheet, you can open it here for saving and so on. Similarly, we have edit here, for undo, redo, and all of these other options. And these are the design source, which we will get into in a bit. And then similarly, we have these libraries, which I will showcase here as well. And then similarly, so here we have our libraries. You can just scroll down, and then you'll see the power RLC branches. You have the resistor, inductor, capacitors, and so on. We have the switches. We have different switch elements, and then in transformers we have many different transformers available, different types of transformers, magnetic elements, and then we have many different control blocks. And these are the different motor, motor elements available. For example, we can just drag and drop here. Okay, so we can just drag and drop anyone, and to find out, to know about it more in detail, just double click on it, and it will open up squirrel cage induction machine. So here you have all the parameters that we need to enter. It will all come with a few default values already entered. So to further know more about these in detail, all we have to do is click on help here. So once we click on help, here you have it. You have the description, you have the parameters, and you have a good amount of theory behind it as well. And then similarly, we have different examples here inside, wherein if you can just click on one of these, it will open it, like as you see here, it will open an example circuit done with this particular model, so for our understanding. So there are a lot of cross linking like this. Here if you go, it will take you straight to documentation, so more theory on it. So like this, all the information that any individual will need to learn PSIM is inside the software itself. So it is that straightforward. Now, similarly, we have the control elements, and then yeah, we have some spice encoder and some more elements here and so on. Similarly, the elements can also be accessed from here. Okay, here from here you can just go here. You can just hold your mouse over it, and it will show, and then so on. We can just go through it, and we can just use any of these. So now I just to give you a brief view or feel of how easy it is to connect components. So we can just drag and drop components here. We can just drag and drop components here, or you have these list of commonly used components at the bottom of the screen here. So we can just drag and drop or just click on it. It will come, and you can just take it and place it here. Now to wire it, to connect the wires, we can just either go to the top of the screen here, and we have this wire option, or just hover our mouse over the components, and this will automatically show up, and then we can just make the connections here. It is very smooth. It is very smooth. And now to get these components, we need not have to go here and search or drag and drop each time. So PSIM has this feature called as hotkeys or shortcut keys, wherein we can just by clicking the key on the keyboard, the component will show up on the screen for us. So for example, if I want a resistor, I can just click R, and a resistor will show up here. And then if I click on I, and then an inductor just showed up here. So like that, there is a list of inbuilt, how do I put it, uh, keys which are already embedded with that particular function. We can change it as well. And then similarly, while moving at one stretch, we can do a 90-degree turn here, not more than that. So even though technically, so long as the circuit structure is the same, it will work no matter how the positioning is done. Ideally, it is recommended to do it in the shortest way possible. Like if we know the structure of a circuit, then it is best to do it exactly like that, so that the wiring becomes easier and debugging becomes easier as well. All right. And then now similarly, we have this, like if I want to like place a component in the if I want to place a component here, for instance, I don't have to delete this wire and then bring a component and place it here. I can just take this and I can just drag and I can just put it there, and there you have it. We can you can see that it's there. So it's very smooth to use. And then similarly, if I want to remove a component from here, I can at once I can just take it here and take it out as well. Or we have this feature called as rubber band setting. So if we just click shift and move it, then it will move with the wire. So depending on our application, we can do it. So all of these can be changed by by features, by options available in settings and so on. I won't get into too much detail right now about that, but it can be changed through settings. All the rubber band setting and your customizing your keyboard and so on. Now, just to give you a few small simulation examples before we get straight into the design source. Now, yeah. So this is just nothing but a simple RLC circuit, as you can see. So we have a resistor, and then we have an inductor, and then we have a inductor, capacitor, and then we have these voltage probes. These voltage probes come in like two types. Like initially, we can use this voltage probe as well for a single node, or we can from the bottom of the screen between two nodes. We can bring this as well. So to rotate it, just click on Control R, and it will rotate, and you'll have. So we can do this as well. So now this is to simulate, we need to bring this option called as like simulate controls, that we can set the time for how long this circuit should simulate. And then here, so here you see this in the resistor and inductor itself, you see this these flags, these voltage flags and control flags. So these serve as inbuilt probes. So we don't have to connect a probe externally for this. Here it is internally connected. So wherever you see a flag option like this in PSIM, we wherever it is 0 it is disabled, and whenever it is 1 it is enabled. So because it is enabled here, it's on 1, we'll be able to see it. If it was disabled, then once we simulated it, it wouldn't show. Let me just show it to you. This is 0, and I'm disabling it. And then, yeah, now to simulate, you can just go here and click, you know, uh, now the software is simulating, and you can see the outputs are just V in and V out. So this is how you can, you know, there are a lot of post processing options here, which you can, yeah. So since this is a simple RLC circuit, the output and input are meant to be the, yeah, sorry about that. Yeah, it's meant to be the same. So now we want to enable these probes. So if I just click on one here, it'll get enabled. And so now once we simulate it again, you can see the output here. We can see this voltage of R1. It is there for us to see. And then similarly, we can see these other ones as well. Yeah. And now to just to zoom and zoom out, we can just use this. We don't need it here, but I'm just showing you. And then this will once you just keep your mouse over it, you'll know what exactly it'll do. So this is auto scale the y-axis, and this is to just pan around, move around, and then so on. So now saving is as you do in any other software. Just go to file and save as that. Yeah, that is as usual. And now, if you for your output, like for your report formation, if you want to, take this, convert this into a report, then you can just go to edit, copy to clipboard, meta file format. And after we do that, you can just copy and paste it in Word file, and that will a Word file or PowerPoint format or anyhow, that is, so it'll look like this basically. So similarly, we can do the same from the post-processing outputs as well. Yeah. So similarly, we can go here as well, and or directly we can just right click and copy to clipboard and meta file format and do the same thing. So this was just a brief about the main functions that we use to set up a circuit and then to simulate and then to analyze and so on. And this is just another simple example of a buck converter, which we can see here. And then we have a DC voltage source with an amplitude of 100 volts. And then we have a MOSFET, an ideal MOSFET, an ideal diode, and we have an inductor with 100 microhenry, and then we have capacitance with 100 microfarad, and we have a resistance of 12 ohm, and we have two voltage probes as well for voltage in and voltage out. And finally, for the PWM generation, the gating block, we have this gating block G1, so 0 and comma 180. So the duty cycle will be 50%, 0.5, and then we can simulate this as well. We'll just close this. So we just close this, and we can see these as well. So the simulation time, as I mentioned to you, it can be set here. It can be adjusted here. The total time of the simulation. So here 1 second. Now similarly, as it is simulating, we can see the outputs live also. Now if I just simulate it again, if I had the if it simulates for longer, which I will show it in a different simulation. So once it simulates for longer, you can actually see the each simulating live. So then this was about the simulations and how we can do it in PSIM. Now we'll go straight to the design source. And yeah, so this is the different type of design source that are available inside the software. We have a buck converter, boost converter, flyback converter, full bridge, resonant LLC, and so on. So just to show you an example, so this is the buck converter, and we just clicked on it, and we have our entire circuit ready for us. So you can see these variables here. So all we have to do is enter these input values. So once we've entered these input values, we can just click on update parameter file, and we can just simulate basically. It will the software will simulate for us. They do all the work for us. So now here you can see at the bottom right corner of the screen, as the simulation is running, and you can see the live, you know, the value being generated, calculated by the software. So this is during the simulation. So once the entire simulation is completed, of course, we can see the final, in the different appearing post processing scene. I mean screen. So here it's done, and then we can see, and we can analyze. We can So all of that can be done later. So this is how smooth the power supply. The design suits will do it for you. I'll just show you one more, motor control and the motor drives and the motor control design suit, and then I think we will get to the Q&A Q&A stage. Now coming to these design suits in motor control design suits. Initially, I'll show you the different motor drives that are available here. Yeah, this I showed it to you already. Yeah, the different PMSMs, the brushless DC machines, and six-phase synchronous machines. If you can scroll down, you can just see the sheer amount of motor models that is available in the software, and these are different control logics components that are already in the software. So you don't have to manually do this. So you can just drag and drop, and we can just use it. So now coming to the design source, if you just go to design source, and then you can see all of these, PMSM, IPM drive, and then so on. So now we're just going for the FOC controlled circuit. So here, if you go here, this is just zoom to fit page. Here you can see your inverter. You can see your input DC bus voltage, and then you can see your three-phase current probes. You can see our PMSM motor here, and then we can see our load. And so this comprises of our entire power stage part. And then coming down, we have our control stage design here, the FOC logic with the forward and reverse spark and clock transforms, and with all the sensors. So you can see these blocks are available, like inverse spark transform, DQ to alpha beta. So with these blocks, the FOC has been logic has been entered, and so we'll just be entering these: the DC bus voltage, the switching frequency, the load, the motor parameters, and few of the controller parameters. And then all we have to do is click on update parameter file, and here you can see here the software will show you all the parameters what we entered here: the DC bus, and the motor, the back EMF, constant number of poles, and so on. And then it will show you what it has calculated as well. So inverter maximum inverter AC voltage, the calculated torque, similarly the controller, the PI gain, the PI time constant, and so on. So all of these, the software instantly calculated it for you, and it entered it into the circuit as well. So now all we have to do is just run the simulation. You can see how fast it is simulating. Once it's simulating, you can just view and view whichever outputs you want, and you can further analyze. These are just the three-phase currents. So similarly, the other design suits work as well, and there are many additional features like high fidelity cable models and sensitivity analysis. For the design of experiments can be done with the software known as hyper study, wherein basically we just vary one parameter. We can keep a few parameters constant and vary one parameter and run like hundreds of simulations in a very short span of time. And that can be done by co-simulating with hyper study. So that is what we're actively working on right now. So this was about the webinar for optimizing power supply design with PSIM.